Hello, and welcome back to the Honors Pre-Calculus video tutorials for Mr. Billingham's Honors Pre-Calculus class during the COVID pandemic. I hope you're all staying well. Today we're going to go into part 2 of 10.5 Statistical Literacy, and the topics we'll be covering today are samples, surveys, and observational studies, experimental design, using randomness, and simulations. Now this is going to be a fairly lengthy section, but I didn't want to break it into two, so I'll see if I can get it done in one video tutorial without being too long. So our first topic, samples, surveys, and observational studies. Recall that statisticians use statistics, which are numbers determined from samples, to estimate parameters, numbers associated with populations. You might think it'd be safer to gather data from an entire population, in which case the study is called a census, but that's often impossible or at least impractical. Instead, statisticians pay attention to their sampling methods so that they can use the laws of probability to make confident inferences about population parameters. Some sampling designs can be quite complicated, but the most basic requirement is that the sampling be free of bias. That is, there should be nothing in the sampling process that could systematically cause the sample to differ from the population with respect to the statistic being gathered. Sadly, biased sampling is one of the most common flaws in the world of bad statistics. Each of the following studies suffers from a form of sampling bias. Point out the problem, and we'll then give it a name for you. Number 1. A local talk show host wanted to assess the opinion of city residents on a proposed tax increase for public education, so he invited listeners to phone in their opinions. According to his poll, 93% opposed the tax increase. Well, I suspect you have some sort of a sense about why this has bias in it. For starters, the sample was not likely to include anybody not listening to the show. This is called undercoverage bias. Undercoverage bias is when the entire population is not randomly sampled. In this case, we're only sampling a small subset based on those who are listening to his show. Secondly, listeners had to be a little fired up already about the question to go to the phone, and coming out against a tax increase fires people up. This is called voluntary response bias. The 93% number had to be likely much higher than the population. So our first example had two types of bias. Undercoverage bias, because it only sampled people who were listening to that show, and that left off all the people who weren't. And secondly, a voluntary response bias, because the members of the sample are volunteers. They volunteered to answer it, so they kind of had some skin in the game, as it were. Let's look at example 2. A parent group opposed to the proposed renovation of their school auditorium passed out a questionnaire at the football game with the question, should the school jeopardize vital school programs by diverting funds to improving an auditorium that is needed only a few times a year? They reported that 89% of the people were opposed to the renovation. Well, sampling at football games is another source of undercoverage bias, because people who aren't at the football game don't have a chance to be sampled. And people who are more apt to go to the auditorium might be less apt to go to the stadium. Also, just passing it out at a football game because everyone's there is an example of a convenient sample. The question itself also created bias, as the wording was designed to provoke a negative response. Read the question again and notice the negative words. Should the school jeopardize vital school funding by diverting funds to improving an auditorium that's only needed a few times a year? Notice how negatively it's phrased. That's an example of response bias. It's the wording in the study is designed to influence responses, and that is response bias. In this case, the 89% reported is likely much higher than the parameter, the true level of support among the whole school community. In number 3, seeking feedback on their new toothpaste flavor, a company supplied 500 dentists with free samples to give to their clients. With each sample came a stamped postcard with a single box for the user to check. Like the new flavor or don't like the new flavor? The company received 897 postcards back, 85% of which reported that the user liked the new flavor. In this problem, undercoverage was probably not a problem if the 500 dentists were a representative group. Now, it's true that people who didn't go to the dentist were underrepresented, but they're also less likely to buy the toothpaste. So that was probably fine with the toothpaste company. The real problem here was response bias, as the company may have unintentionally elicited a favorable response by giving people free toothpaste. At the very least, people who slightly disliked it might have been less inclined to send back their card. More voluntary response bias here. The 85% approval is probably higher than the parameter in the real population. Number 4. A biologist wanted to gather evidence that nuclear power plants caused genetic defects in frogs that fed in nearby ponds. He sampled 50 frogs in a pond near his local nuclear power plant, discovered that 8% of them had genetic defects. This was in fact considerably higher than the rate in the general frog population, so he considered this to be good evidence supporting his assertion. Since the scientists only took samples of frogs from a single pond, it's another convenient sample. Also, think about it. The frogs he was able to catch maybe were easier to catch because they had a genetic mutation, so that was far from random. These frogs did appear to have a problem, but the fact that they all came from the same pond makes undercoverage bias a strong possibility. There are many other possible explanations other than a nuclear power plant for the high defect rate in the sample. Perhaps there was pollution, chemicals in the water, we don't know. In an observational study, data are simply observed and recorded. Often this does not involve sampling a population at random. For example, in a wildlife study, scientists have access only to the animals they're able to observe or capture. Other researchers may gather information from such available sources as doctors' records, census data, or the internet. Often, observational studies suggest the presence of important associations between variables, but they cannot prove causation. And the lack of random sampling dictates caution when trying to reach conclusions about an entire population. Observational studies are certainly useful, and it is possible to draw conclusions from the data up to a point. For instance, observational studies suggested for years that there was a high positive association between smoking rates and lung cancer rates, but this didn't prove that smoking variable cured an increase in the cancer rate variable. No, indeed, there was also a high positive association between coffee consumption and lung cancer rates. Of course, many coffee drinkers used to enjoy a cigarette or two with their coffee. To actually show causation, researchers must control confounding variables like coffee drinking. This requires experimentation. A well-designed experiment can show that there's a cause and effect relationship between two variables by accounting for all other possible explanations. In an experiment, researchers impose treatments on subjects who are often volunteers. Each treatment is based on factors that might affect the response variable under study. By controlling the factors, the researchers hope to identify with high probability a causal relationship. There are 4 important principles of experimental design. Number 1, control. Variation between subject groups receiving different treatments should be limited to the factor we're varying, while other conditions are made as similar as possible. For example, if we're testing the effectiveness of a drug, everyone should get a pill, but only one group's pills would contain the drug. The fake pill is called a placebo. The experiment should be blinded. Neither the group nor anyone who has contact with them should know which treatment they are getting until after the data are collected. If the experimenter also doesn't know, that's called a double blind. Randomization, number 2. Subjects must be assigned randomly to the different treatments so that variation arising from uncontrolled and often unknown factors will be spread out randomly among the different groups. Replication. An effect should be observed in multiple subjects, the more the better, to be statistically convincing, and other researchers should be able to perform the same experiment on subjects from the same population with similar results. Finally, blocking. As a form of control, pre-existing differences between the subjects we might think might adversely affect the response variable, like gender or lifestyle, should be deliberately spread evenly but at random among the treatment groups. For example, if there are 10 women and 40 men among the subjects for a two-treatment experiment, and we believe that the men and women might respond differently to the treatments, we would want to randomly assign 5 women and 20 men to each group. If men and women did react differently to the treatment, we could take that variability into account when assessing the effects of the factor under study. Let's use these principles to design an experiment. A researcher wishes to test the effectiveness of vitamin C supplements for preventing flu. He has a diverse group of 200 men, women, and children who have volunteered for the study. Design an appropriate experiment that takes into account the likelihood that flu will affect different age groups differently. There's only one factor requiring two treatment groups: supplements and non-supplements. A simple way to control for the age variable is to match volunteers of like ages together, then randomly assign one from each pair to each of the two treatments. This spreads the age variability equally between the two groups. One group will take tablets containing vitamin C, the other group will take placebos. The subjects and their caregivers will be blind as to which tablets they're taking. We monitor each group during flu season, record who gets the flu. Here's the design of the experiment. So begin by pairing the 200 people by age. For each pair, randomly assign one of the pair to group 1 and one to group 2. In group 1, you get treated with vitamin C. In group 2, you get treated with a placebo. You wait out the flu season and compare flu rates. In example 5, you'll have an opportunity to analyze experimental designs. Each of the following experiments suffers from at least one flaw in design. Identify the flaws and tell how each experiment could be improved. In a study of multitasking, psychologists test the time it takes a group of volunteers to type the same 100-word text message, first listening to loud rock music, then listening to soft classical music, and finally listening to no music at all. Here are the flaws. Since the text message is the same each time, the texters are likely to pick up speed as they gain familiarity with it. The researchers should either work up 3 different 100-word messages or else randomly assign the music treatments in 6 different orders: rock, classical, none, rock, none, classical, etc., and average the times. Number 2. To test the effectiveness of an expensive online homework service, a teacher with 2 sections of freshman algebra signs up his 30 A period students for the service and teaches his 30 B period students the same lessons but without the service. At the end of the year, he compares the grades of the 2 sections on the same test. What's wrong with this one? The subjects aren't randomly assigned, so any differences in test scores might well be due to other variables. For instance, is one class in the morning and the other in the afternoon? They might be tired differently. Were all students taking an advanced science course that will force them into one of these 2 sections? The teacher should randomly choose 30 of his 60 freshman algebra students to use the service, without regard to which period they're in. I'm not quite sure, though, if he did that, how we would teach the other 30, because they would be only half of his classes. Number 3. A drug company tests a new pain reliever on 100 arthritis patients, which it randomly splits into 2 groups. Half the patients are given the new pill, while the other half are told to continue their regularly prescribed medications. After 60 days, the 2 groups are interviewed by representatives of the drug company to report their level of pain relief. Here's the problem with that one. The biggest flaw is that the subjects know which treatment they're getting. Those who get the new pill might feel better simply because they think they ought to feel better. The pills should be made to look the same so the subjects don't know if they're taking their old medication or the new one. A second flaw is that the drug company representative might unintentionally treat the subjects differently if they know which ones took the new pill. The person who interviews the subject at the end of the study should not know the subject's treatment. An experiment, again, in which both subjects and data gatherers are blinded is called a double-blind experiment. Well, I had originally hoped to finish the material there, but it's 15 minutes already, and I think any longer than that's just too long for one video. There's a lot of material in this, but it'll be very useful in answering your homework. So look over it again, make notes. I've tried to hit the key terminology and concepts, and see you in the next video. And it is, it's sad not to be together in the classroom. I hope you're getting something out of these videos. I've gotten a number of very kind emails from folks thanking me for them, so I do appreciate it. The BC guys have been sending in memes, and I've been including those in the video lectures. If you guys want to come up with some memes, I'll do that for you too, or anything else. If you've got good jokes you want me to include or anything like that, just something to make it a little more interesting. Anyway, until next time, bye-bye.